Clear.
Okay, thank you. So let us start the class because any class on analytics, mathematics, and statistics, they take their own time. So let us start. Okay, a brief. So far, how many participants? I think only 36.
36.
Okay, okay, fine.
They may join, sir.
Okay, fine. Let us start it and let other people join in between.
Yes, sir.
Yeah. Thank you, Dr. Venugopal.
Thank you, sir.
Good morning once again to everyone. Today, we are going to discuss in this particular session the forecasting models. Let me tell you from the beginning that it's a very vast topic, and we have been given, looking at various constraints, we have been given 2 hours. So during these 2 hours, I'll basically talk about the forecasting models with respect to the time series. Okay. There are other cross-sectional things also you can try, like you can say OLS based regressions, then neural network based regressions, and so on, logistics based regressions. So you can try with the cross-sectional data and even for the time series data. But basically, I'll be focusing on few methods in the forecasting. Those who are already there, they will have some take home. Those who are basically starting also, they will have at least certain things so that you can take it further. This is a very nice and interesting topic. So it's all our interest because without forecasting, no business organization can really survive. We need to have some forecasting, even though it is incorrect, right? Even though it is incorrect, even though it comes with a lot of inconsistency or whatever. You need to have something. It's like uh, you know it's like something is better than nothing, right? The current situation, how things are happening. Even there also we are having some forecast, even though it is coming incorrect. So some forecast, if you can do it, that will really help the research or maybe the organization or the firms to basically proceed further. Had it been manufacturing, had it been services, or any other econometric kind of models and related aspects. So we need some kind of forecast. So basically, I'll be taking you through the presentation initially, maybe for you know for 30-40 minutes, and I'll give you the some insights what is essential, and then later I'll get into the hands-on part of it. There are two types of hands-on I have just kept, but I'll simply demonstrate by the running the course and what is expected to do that. Typing the codes and all that will take its own time. So we can't even complete a part of the say the concept what is expected to be completed. So with that note, let me start. And we have so far 45 participants. So I'm just starting. And some of you maybe from econometric backgrounds. I think some maybe from purely from data science background. So you may be, will be adding to your, the concepts, and those who are especially starters, they will also have, especially the research scholars, will have a lot of insights from this particular class. That is what is my understanding. So that note, let me start. I hope my screen is visible.
Yes, sir. Yes, sir. It is visible.
Okay, fine. So let's start. Uh, so I'll just give you a little overview of the forecast. Uh, I think this is my second time I'm delivering a lecture at IIPMB. I thank Dr. Venugopal and Dr. Ganesh for the opportunity. I think last time I delivered on the machine learning, this time purely on the prediction. Okay, so here actually the forecast is, we all know that it comes with an error. Okay, no matter how best you treat the data, right? No matter how best you treat with the data, there will be some forecasting error, right? So future is uncertain, and no matter what technology, what insights or techniques, whatever we have, there will be some forecasting error. But as a researcher, as as a data scientist or maybe whatever, so we need to minimize. We just need to minimize because that is one thing that we probably can do with our all sophisticated techniques and all that. But irrespective of all this, there will be some error. There will be some error, but less than 20% of the error will be basically better. So 80%, if you are able to forecast your data or the scenario, I think that's a good one in terms of the forecast. So basically, what happens in terms of the forecast, we take the time series data for the forecast, and there you have a lot of techniques available, starting from the basic methods like moving average, exponential smoothing, then the Holt's method, the regression based methods, all those are available. So I'll try to cover a few of those methods in my in Python. And one of the methods, that is Holt Winters method, I'll just demonstrate in the Excel, so that you also can calculate certain things and see how things are really happening in the Python codes. Okay, that is very important, because running the codes, you just see the result, and we are not really developing any kind of algorithm to develop the forecast. We are just trying to run those codes, because we are not the developer of any algorithm, right? We are just users of it. So for that, what is really happening at the background, we are really or maybe sometimes we are not aware of it. So if you can do it yourself in the Excel, okay, manually, maybe whatever wherever it is possible, then probably you can see what is expected in maybe Python or R or any of the softwares. So you know that there are some software that are very user friendly, and some softwares like Python and R, you need to have little bit of coding. I think Dr. Ganesh might have given you some insights on Python, but given the time frame and the duration that you have, I've seen the schedule. It may not be possible for him to cover much things. But anyways, so you can those who are starting, maybe this is the starting point. Please continue your learning, and wherever it is possible, please be in touch with us. We will also help you. Now, the forecast, basically we have three different types. Okay, whether you are doing something for your HR planning, or you are doing for your manufacturing, or somebody is the projecting the growth rate of a typical country or a state or whatever. So you have different types of forecast that we have. So based on if you are from business, or maybe if you're from economics, or maybe related background, you may be knowing that there are three different levels, okay, in the organization or the firm. So purely the people who are at the shop floor, or who basically produce certain things, okay, they are basically you can say the operational people. They are the operational people who basically do the things at the ground level, whether it is a product or a service. So they do that, right? Secondly, that you have is the upper level is the tactical level, where you have the managers and the assistant managers, the supervisors or whatever. So they will be there. Let us say the second level, maybe a little higher than, you can say, maybe supervisor or manager and above. Okay, but less than general manager or something. Then the top level could be general manager and above. So this is what is the hierarchy that is basically maintained in any manufacturing or the service-based organizations. So there, looking at the requirement, If I say the top management, or the, you can say, the managing director or the chairman of a company, they're interested to set up a company, or maybe a new plant or a warehouse or whatever, or somewhere else. So this is basically a very, very long-term plan, right? So you have a lot of investment, some hundreds of crores maybe invested in the process, and after that, once you take a decision to have it, you cannot probably go back, right? So there may be a chance to lose a lot of money if you take back step. So here actually the a lot of analysis of these scenarios and all that you need to do. So this is basically 5 to 10 years. Okay, but you can say it is 50 years or 100 years or whatever that may be there. So the next level is the tactical level. Basically, if I give you a small example, maybe it will be more clear. So they're actually, let us say, manager, or maybe lower than general manager, you can say assistant general manager or whatever. So do in that level, basically what is done is, so you may need to identify the suppliers, okay, and you may need to deliver the the supplies to your buyers or whatever. So maybe the bigger plans that you need to do, okay, but operational people will be giving the shape to it, they'll be doing it, and the tactical level will be probably coordinating with other people outside, and it will be delivered. So depending on the requirement part of it, so your requirement for the data may change. Okay, it may be for 1 to 3 months, basically for the short term planning, that is, you can say, at the operational level, and the medium term is for the tactical level. Mainly we say this is something called as in the production we say aggregate plan. We say basically aggregate plan. How many workers? Okay, what is the kind of material that we need to procure? What will be the machine capacity? Okay, so all this will be finding. Okay, so maybe in certain times you may feel that I'm little biased towards the manufacturing or the production, being a person from operations and mathematical background, but this is what is something that we have. Okay, you can emulate to any field, doesn't matter, agriculture, services, economics, computer science, wherever possible. Okay, we can emulate these things. So this is actually the thing that we need. This is the data part. Now the question comes here is, what is the right size of the data for doing this exercise? So that actually depends. You may have to refer your subject matter, or maybe the previous authors or the researchers who have already published. Uh, Basically, what we take is 10 years of monthly data. 10 years of monthly data will be okay. Will be okay to run a kind of a ARIMA model or whatever. Right? But bigger is the data size, better it is. But that again depends. Okay, it certainly bigger is the data size, bigger is the representation. That is the your pure research methodology kind of practice. But we need to refer to our earlier literature. Okay, and we can say that we can see what would be the best data size, or maybe there is nothing best in this case, I should say. So there is, what is the appropriate data size, right? So I'll be demonstrating the data size for the last 10 years. That is 120 data points. That is actually the data that is part of my research, and I have downloaded from several fields. I'll just show you. So you'll have a little insight, and that is purely on the food. Then here actually this is very interesting, the aggregated forecast and the disaggregated forecast. Okay, so the aggregated forecast is something that you have you can say the short term forecast, or the short term data that you have, and you keep adding, so that becomes the aggregated data, right? Like a bigger data set. This bigger data set, if you go for the forecast, so that forecast, you may find your forecasting error and other things, and you divide according to the requirement, and you go for the forecast. Now which is better, which is giving more error and all that probably can be seen, but it has been seen that higher is the data size, as I said, so better it is. So that is why the aggregated forecast are often better than the disaggregated forecast. But for the information of the people who are from marketing, maybe supply chain and so on, so there actually one thing we say, data, or market segmentation. So market segmentation actually is very crucial for a manager to understand what is the segment and what is the requirement of that particular segment, right? That we say, when you talk about this, why we are interested in this, you can say it is a disaggregated forecast. But why we are interested in this is because we need to understand the implied demand uncertainty, right? So something called demand uncertainty and something called implied demand uncertainty. So why it is very very important to understand, because the aggregated demand has an average and also a standard deviation, right? Similarly, when you go for the disaggregated data analysis, there also you will have averages as well as the standard deviation. So there are a lot of things somebody can calculate statistically to figure out where the inconsistency is very high, where the consistency is better, and all that. So that accordingly the managers, or you can say the people who are at the helm of affairs, they can probably take a call that this particular market is behaving in a certain manner. So these are actually few things from the viewpoint of the marketing, maybe from economics, maybe from the viewpoint of the supply chain and the operations. People basically need to understand those things. Okay, so irrespective of the error or whatever, there may be a need to go for the disaggregated forecast. So disaggregated forecast may give you more forecasting error, but still it will give you some kind of insights, and that insight will definitely help to take better decision. Now, the thing is that there are few methods available, and the more you learn, the more the new things will be coming to your mind, and you will be really enjoying this, right? So let me give you a little insight here. People who are, let us say, starting, so they can start from the moving average. It's a very simple method. Then comes exponential smoothing. That is also relatively a simpler method. Then comes regression. Everybody is familiar with it. Then Holt's and Winters method, a little standard. Then ARIMA, auto-regressive integrated moving average method, auto-regressive integrated moving average method with the exogenous variables. Okay. Then we have several types of neural networks. Okay. Then several other things. Even in the neural network, you can also have several time series analysis where we can get into those who are maybe from computer science and mathematical background, maybe knowing of something called the Fourier transformation. Okay. So all this there we basically take into consideration sine and the cosine kind of trigonometric functions, and we basically design our time series. So these are actually, the more you get into the literature, and the more you get into the concept, the more you learn, and you can execute in R or Python or whatever, MATLAB, whatever. So these are the few things that are available, and I'll be covering few of the methods that you'll have reasonably a good experience in the class. So then little bit of forecasting requirements. I'll not spend much time because already it is 10:20. So the components of the forecasting, that you have a systematic component that we calculate, and there is random component that is actually our that is like our error, right? So here you have the systematic component. How we calculate basically is the level that is basically calculated from the data with some algorithm. Okay. Then the trend, whether it is increasing trend or decreasing trend, or it is stable or relatively coming up with a stable fluctuation, that you can calculate. Then the seasonal fluctuations will be there. Seasonal fluctuations, you can say from period to period, right? So let's say quarter 1 to quarter 2, quarter 2 to quarter 3, January to, let us say, March, and April to June, and so on, right? So all these kind of fluctuations will be there. They are basically the short-term fluctuations, and the short-term fluctuations that you can calculate with respect to the seasonality. And there you have the multiplicator. There are basically the three. There are basically three different types of models available. Okay, you can go ahead with any model depending on the literature support, or your perception or your hypothesis that you can adopt. So you have the multiplicative model. There actually what we do is what is level, what is trend and seasonal factor, that I will demonstrate in the Excel sheet. So for the time being, you just see level means what initially you calculate, then trend is whether increasing or decreasing, then the seasonal factor is the fluctuations. Right? So these are actually the data decomposition part. So data decomposition. So once you do that, you'll be able to see how things are happening. Then is the additive model. You have the same thing. You are just adding all of them: level, trend, and the seasonal factor. And the next model, this is actually used by the Holt-Winters method. So this is actually mixed method, always, or maybe most of the times better than other kind of models. There you have the level plus trend. You are adding level, what is the initial value, then the trend, then you are multiplying with the seasonal factor. So this is another model that is available, right? So these are actually the the things that are required for the systematic component, and for the random component, that is nothing but your the residual part of it or the error part of it. Okay, so how far it is deviating from the the actual, like how we do in the SSC or MSc or whatever. So then quickly getting into the model requirements, I'll not be able to spend much time on these things. So the moving average, you just add, it's like your, averages. You know how we calculate the average? We add all of them and divide the total number of observations. If it is, coming up with some weight, if it is coming up with some weight, so that means that weight has to be multiplied with the respective observation, and the denominator will have all the voltages. So sum of all the voltages is equal to 100%. That you may be knowing. I've written here. So this is actually the weighted moving average. If there are weights are all equal, then it will be summation of WI is equal to it will be 1, right? That is weighted average. If it is n, then it will be simple moving average. So total by n, like our simple thing that we do, that is this is a summation, this is summation of x is equal to our x bar is equal to summation x by total number of observation. If you multiply w here, then it will be summation w, right? It will be summation w. So this is what it is. It is a simple average formula. Now the little advanced thing here is basically, if you want, after you predict and you want to optimize your weight. Okay, so those who are familiar with linear programming, so there what we can do is basically we can optimize the objective function taken into consideration with respect to the mean absolute percentage error, or maybe some error if you want to take. Okay, and the weights we need to these are the weights subject to that w1 plus w2 plus up to wn. If you have n number of weights, that will be equal to 1. That is one constraint. So you can solve it and see your weightages are now optimized. Weightages are now optimized. This is additional thing, maybe for some learners will be helpful if you are doing it in the Excel sheet. I'm giving you certain insights, but I'll not be executing it in the Excel because of the time constraint. You can get into it, you can practice it at home, taking a dummy data maybe from Google or maybe from somewhere, and do it yourself. In case you have any queries related to this elementary methods, I should say these are the elementary methods, and everybody should be familiar with this, because as far as the forecasting models are concerned, these are actually very, very useful. And uh, one interesting book that you also can follow, that is by Mukredakis. I have mentioned at the end, for economics people, econometric people, data science people, computer science people. That's a very nice book, and that is the new version is coming up with the Hindman. That so that is actually will be giving you the exhaustive ways of learning the forecasting models. Now you can integrate with your machine learning, in Python or whatever. So, but domain is very crucial. I basically emphasize on the domain part because the software part is one thing that probably you can just pass your model or maybe data, and you can train your model, you can test your model. That is one thing that probably can do. But what is really happening at the background, the logical part of it is very, very crucial. Okay, if you do not understand, so probably as a researcher, I should say that we should understand what is really happening, not at the algorithm side of it, but the domain part of it, because we need to draw inference end of the day. And if you are a researcher, you are a faculty somewhere like us. So our interest is to publish in a good journal, and you know how difficult it is to publish in a good journal. So we need to be very, very then comes the exponential smoothing. There you have, it's like a regression-like model available here. So that is, this is the forecast that you are doing it for, for the time that is t plus 1, and your data is available till t time t, and you take here one thing that this is actually your actual demand. You are giving some weightage, and you are giving some weightage to your forecast, right? So now the question comes is, what is the weightage that you should give to your actual demand, and what is the weightage that someone should give to this forecast? Now the question is, if you're doing it in Excel, then you can do it and figure out what is your alpha, and depending on your requirement, you can change your alpha. And if you you work in the forecasting for several years, you have some experience, then probably you can what could be how to change the alpha, and how to what would be the best result. But in case you want to optimize that, also you can optimize by using linear programming. So how you can do that, I'll demonstrate later. So this is actually one thing that is possible. So these are actually few things. Now people who are familiar with it, why this method is called as exponential smoothing method. Okay, there is no exponential term here, as you can see. Okay, there is no exponential term here. It is only alpha dt plus 1 minus alpha ft. So one is the forecast that you calculate, and the one is the demand that is already available. So where is the exponential term? So exponential term comes from the concept. Suppose you are calculating ft plus 1, then you are using t here also t. If you use ft again, if you calculate ft will be alpha dt minus 1 plus 1 minus alpha ft minus 1. Likewise, if you proceed and substitute, you will see that there will be one alpha term, there will be one alpha square term, 1 minus alpha whole square term. That means alpha, if you take, is a value ranging from 0 to 1, and alpha into 1, so let us say 0.5. 0.5 into 0.5 will be 0.25. Okay, likewise 0.25 into 0.5. Okay, 0. Let us say 0.25, 0.125. Likewise, things will change. So what you see is that gradually your older values will be diminishing. Older values, their values or their weightages in the model will be diminishing. That is why this model is called as exponential smoothing model. Then little refinement of the exponential smoothing model is the Holtz and Winters model. So there what you have is basically two in the Holtz model will be using two smoothing constants. There again varying between 0 and 1. But in Winters model we'll be using three different smoothing constants, right? And if you are doing it manually, you can optimize. But in the in a Python codes, they will be optimized. But if you are doing it for your practice to see what is happening in the Excel sheet, you can do it and you can optimize. Okay, how to do it. You can go to the solver and do it. Okay, solver is available in Excel, so you can do that. Then what happens here is your alpha and beta, and here alpha, beta, and gamma. Right. So the refinement of the model, you will be looking like this. Here I have given little insight for the LPP. This is the linear programming model, little bit smaller model. So we are minimizing MAP, and subject to the restrictions or the constraints that alpha, beta, gamma is varying between 0 and 1. Okay, inclusive of 0 and 1. So if you can do that, then it is a non-negative restriction is also fulfilled. So if you have you can say the linear programming based models, that is default algorithm could be simplex. Okay, simplex method. So there you will be able to calculate. Now the thing here is how do you calculate this? There are three different terms coming there. As I said, this is level. Initially I have shown you. Then what is, I'm not getting into too much details of it because we can't do that looking at the time constraint. So LT plus 1, and this is your level, and you can see there is one smoothing constant here, that is alpha. Okay, and it is same pattern. It is like exponential smoothing is followed, like alpha dt plus 1 minus alpha eft, right? Similarly here you are fitting another exponential smoothing model. There I'm basically talking about the Holt-Winters model. That is the bigger model, you can say. Then which is addressing all of them, right? Like level, trend and the seasonal factor. So here what you have is alpha, then here 1 minus alpha, here it is beta, here 1 minus beta, here it is gamma, here it is 1 minus gamma. So likewise, if you can treat your data, then your original data is dt. If you can see, your original data is dt, right? Original data is dt, and from dt you are able to calculate all of them, right? So here actually, if you do that, then your data will be decomposed to your trend, your seasonality, and you can also find the residual right, there. So if you can proceed with this, then you'll be able to calculate your, this. You can minimize your MAP. What is MAP and how to calculate manually and how to calculate in Python. I'll be demonstrating. So this is one critical part in the seasonality actually. So what happens here is the you have the data. If the order, or you can say the period that you take into consideration, so that is basically the a complete cycle, a complete cycle. So how many data points you are going to take for a complete cycle? Let us say if you take a quarter, okay, then you can take p is equal to 3. Like after three periods, or you can say after 3 months, the data again repeats. If you take p is equal to 4, then after 4 months it happens. If you take p is equal to 6, after 6 months the data repeats, more or less. Okay, it will not exactly repeat, it may repeat. Okay, that is what is the time series assumption. So if you want to calculate manually, you can do this. It's very simple. I should say the formula not very difficult. You can take p is equal to 4, then you can take it. So p is even, p is equal to 4, p is equal to 8, that you can, p is equal to 12, all that you can take, and you figure out this is like average formula. What is that you are doing is basically first observation, and in between you leave 4 observations, then you go to the fifth observation, so sixth observation, right? So in between you leave 4, because if you take p is equal to 4, then what happens, you take in between all of them and multiply 2 times, divide by 2p to get your this one. But you do not have to do it manually, so I'm just showing how it is calculated. And if you are you are familiar with the things how to calculate all that, it's fine. If not, then probably I suggest you to try an Excel sheet. Your idea will be more clear. Then you do that, and once you calculate this, this is called basically the deseasonalized demand. There will be one data set that will be getting, and your this is your observation, and this is what is your deseasonalized demand that you actually calculate from this treatment. Then you get your seasonal factor. Okay, so these are the few things that you need for your decomposition. Then comes one interesting thing in time series data analysis is called autocorrelation and partial autocorrelation. Okay, so you can calculate by using this formula. So what happens is actually here is suppose this is your one model, which is basically AR model. You can say this is actually kind of AR model, auto regressive. So basically what happens in our regression, multivariate regression or the multiple regression, y is equal to, mx plus c, we just extend to the more number of variables. Y is equal to, we can say c plus m1 x1 plus m2 x2 and so on. So there, if you convert each of the variables to their, to the past values of the respective series, that is y, then it is called as the auto regression. Similarly, you have moving average, where you will take basically the residual part of it. Now you can calculate by taking this. This is like your correlation, the formula. So here, what is that is really happening here? That is this is the covariance by variance. So you'll be able to calculate this coefficient. So there actually we have two different x and y we take, but here it is only y series. So from the y series you are subtracting y bar, and here also you are taking the lag. You are taking the lag, kth lag. So then you are calculating this one. You do not have to do it manually. You can just see what happens with respect to the SCF and PSCF. Similarly, you can calculate the PSCF. Then SCF and PSCF. These are actually, when you get this, the question here is how to draw the inference out of it, right? So the SAF and the PACF. So we have two basic econometric, test, statistical test that will be, performed here, and you can see that at what level they are statistically significant. So what happens here is basically these are actually the correlation coefficients. Yeah, these are actually the correlation coefficients, and this is called as the box Pierce test. That is a Q statistic, and here you have the Lejeune box test. That is a little refinement of the previous one. So now, if you get this, so your null hypothesis is basically the model does not show the lack of fit. The model does not show the lack of fit. So if the p value that is greater than 0.05, then what you can say is basically your autocorrelation is not impacting your data analysis. Otherwise, you need to do some kind of treatment. So what is the treatment that I'll be showing you in the Python? Then what is that is the alternative hypothesis. The alternative hypothesis basically here is the p-value which is less than or equal to 0.05. So what happens there is it says that model lacks the fit or maybe exhibits the lack of fit. So when the model exhibits lack of fit, that means you have to assume that your autocorrelation is very, very high. When the autocorrelation is very, very high, then we basically, in the time series analysis, we say that is, can say the non-stationarity is there in the picture. So we need to control the non-stationarity part of it. We first have to make the data, controlled within the plus or minus, 95%, level of confidence, right? If it is not falling, then the data will be going out of the range. If you are familiar with the confidence interval and all that in statistics, you may be knowing all this. I'm going little, superficially when I talk all this because of the post. So now this SCF and PACF and the requisite test. Okay, there are other tests also. There are few tests like you can say your Jark-Bera test. Jark-Bera test that will talk about the normality part of it. Okay, then the heteroscedasticity part of it. You have some test. You can say the Bruch-Pagan test, and you have something called Hanan-Quinn information criterion values and the respective probability values. All those things will be coming into picture that you can probably learn gradually. And also one thing that I'll be talking about it. There's something called Granger causality, right? Basically, what happens in terms of our models that we have in, you can say whether it is a regression model or maybe autoregressive model. There we basically take how the data is depending on its past values. Okay, if today it is raining, then did it rain yesterday, right? So something like that. So what is the value of a typical commodity price today, and what was the commodity price yesterday and day before yesterday, and so on, right? So this is what is actually when you go back. You can have a systematic pattern, and from there you can have a kind of interpolation to show that this is what is your prediction, and accordingly you can take a decision or the policy. Maybe policy can be taken by the state governments or maybe the central governments to control certain practices or maybe some unethical trade practices, I should say, right? So I'll be demonstrating one interesting case here. So this is actually one thing that when we take this is the common regression, that multiple regression, everybody is familiar with it. I should not explain it. Then what is that we are going to do is, if we can replace the past values of y itself, then the model will be looking like this. So it is a kind of a model that is AR model. So here AR model we have taken up to p lag. Okay, we are going back up to p lag. The p values. You can say if you take this part, then y is depending on its immediate past value. If you take this, y is depending on immediate past and the little before past, so and so on. You can continue that way. And there is another model. This you can say there is auto regression. This is called as auto regression. So this auto regression, why it is? Because y is depending on itself. Okay, and by it's a time series. Similarly, what we have is basically the moving average. Here, the moving average concept is slightly different from the moving average what I spoke a little early. This moving average is, calculating the mean. But here, exactly, the mean is not being calculated. This is something related to the residual or the error. If you model your the y series or the dependent series with respect to the residual by their past value. So let us say if you take this, then immediate past value. Okay, then you take this, then you have two past values and so on. And here actually we take up to basically we take up to q. That's fine. So BP and AT minus P. So to P lag. So here again, so or you can say this is Q and this is also Q. So there is a typo error here. So then ET, then if P is equal to Q, and that must be fine. So this is AR model, this is MA model. Now, if you integrate these two model, if you integrate or join these two model by something called differencing, then you have a new model that is basically auto-regressive integrated moving average model. So how it looks like is I'll just demonstrate. So this is actually, you can see this is actually the model where we have integrated. If you have more interest, please see this particular book. It's a very nice book. I basically refer and very exhaustive. And the new version will maybe with the Hindman that you'll be finding the forecasting methods. So now once you have a background ready, then you can get into any coding part of it. That's not a very big deal. Anyway, we are not designing any algorithm. We are basically using reports to get the results. That is what is our interest. Unless you are from pure computer science background and designing the codes, then things may be different. So this is actually the ARMA model. What is happening? Why it is called as ARMA model? There is, there is no differencing happening here. If you can see my past this thing, so I am just adding these two different models. Okay, I'm combining these two models. So when I combine these two models, this becomes a model like this. Okay, that is clearly visible. Okay, so here I'm just adding this. You can say this part is our AR part, and this part is basically this is actually basically your error part. Okay, this is your moving average part. So there is no differencing happening here. So that is why it is ARMA model. If you add this to AR plus MA, this is becoming ARMA model. Yeah, right. Now, if you want to rewrite this by introducing some lag operator that is called as B of YT is equal to actually YT minus 1. Okay, then B square of YT is equal to B of YT. Then B of YT, right? This is becoming B of YT minus 1. Then it is becoming YT minus 2. So we are just introducing one lag operator. If you do that, then your model will be looking like this. If you have a single lag, then it will go up to this. Okay, up to this. If you are going up to P lag, then it will go up to this. And here, if you are going up to Q lag, then it will be going like this. Now the question here is P and this is Q. So far, P and Q, these are actually the two parameters. P is you can say P is basically decided by the PSCF, and Q is the parameter that is basically decided by the SCF. So SCF and PSCF, these play a very important role here in this particular case for the prediction. Now the question here is how to do that, and that there is the technique that is originally developed by the researcher Box and Jenkins researchers. There are two researchers, Box and Jenkins method. They originally called as auto-regressive integrated moving average method, and there we have several models. Now, do not be under impression that it is one ARMA model. You can have thousands of models depending on your P, depending on your Q. Then, if you difference, as I said, if you have the original series is YT, then you have another series that is YT minus 1. If you take the difference, so this is called as first order differencing, and here we say it is the B. It is capital B. Similarly, you can go for the differencing. If you go for differencing, what happens? You are able to control. You are able to control the. You can say the trend part of it. Okay, there are two things that you difference, and also if you want to control the variance part of it. Okay, the bigness part of a typical cycle. Then what can be done is basically we can take some treatment, logarithmic treatment with base 10, so it will control you can say the height of a typical wave. These are actually like waves. Okay, so wave will be controlled with respect to the logarithmic treatment. Then you can go for the differencing treatment. Okay, so differencing treatment will be basically controlling the mean part of it. Okay, or you can say the mean will be almost fluctuating through a kind of central line. Okay, so this is actually you may say that I'm going at a little higher level or maybe superficial level, because this is what probably I can do in these 2 hours. Okay, so if you have further interest and all that, you need to really get into these topics. Otherwise, this is not going to happen. And moreover, this is not that easy to understand kind of concepts. So then we calculate, the model parameters. As I said, you take the logarithmic treatment. Okay, you take if you want, you can take the log treatment with base 10, and here you go for the the treatment with respect to, you can say, the differencing. Then your data will be now controlled. I'll just show you how it happens. Then the second instance is the SCF and PACF. We need to see how it happens with respect to SCF and PACF. Can you see now? I'll just show you one non-stationary series. This is actually, you can see, it's a very classical series. What you can say, it's a time series data for almost 300 observations. And here you can see, starting from here, and it's like a hillocks. Okay, like a lot of hills are there, and they're how they're fluctuating. Okay, so if you take in that way, then you can see there are a lot of issues with respect to, you can say, this is, if you take, this is a cycle. So here is your with you can say the amplitude. Okay, if you take, this is a cycle, the amplitude is less. Okay, if you take this particular one, this is again less. If you take this particular one, this is slightly higher. So amplitude is higher, and also there is a trend. Also there is a trend. It is increasing trend. It is increasing trend. So trend is increasing. There is a fluctuation. So that you need to control by some treatment. If you don't do that, then what happens is the series will be non-stationary, or you can say the non-stationarity. Also there are certain tests that is, we say, decay flow test and advanced decay flow test, ADFs and all that you can also try, that contains the unit root test that we have. So when you do that, then your series will be controlled. So how it will be controlled? You can see now, this is actually after the data transformation. So after the data transformation, all this now is fluctuating through mean, to the mean. So that is 0, and you can say this is your 95% level of confidence. This is actually your lower control limit, and this is your upper control limit. They are calculated, you can say, C sigma by square root of n, and this is plus or minus. So once you do that, you will be getting your upper limit and the lower limit, and the data is now the transformed data. So it is called as you have seen already that the variance or the variation from cycle to cycle has got reduced, even though they are there, but they are under control. Similarly, the trend that also got reduced. So differencing will control the trend, and the log treatment or maybe square root treatment or maybe something else, that will reduce the variance part of it. Okay, so this is what, if you go for, then what happens is that you can calculate the SCF. So non-stationary series SCF, if you go for, then you see that this is something called lag. This is something called lag. This is first lag, second lag, third lag. So if I say yt is equal to function of yt minus 1 up to yt minus 2 and up to yt minus 5. So up to fifth lag. So there is a fifth lag here. So similarly, sometimes we may need to go for higher lags, 20th lag, 25th lag, and so on. If you see that, so this particular thing, if you see, let us say this is 21st, 22nd, 23rd, 24th, and 25th. Till 25th lag, the values are not still under control. It is outside of the range. So this, you can say, this is upper control limit, and this is called as lower control limit, right? So this is actually is a matter of concern. So we say the data is non-stationary. Data is non-stationary. So non-stationary, to make it stationary, you have to have those treatment. Also, you may have some test to see to that how things are happening. I have already told box Pierce test or maybe lesion box test. Those things you can probably perform to see how things are happening, and also certain model parameters that I'll just show you a little later. So here actually what is happening, PACF, partial autocorrelation, you can see now there is something very, very outside of the model. So these are unexpected things that are happening here, we need to somehow control. So how to control? If we use some data transformation technique, then it will be under control. You can see now this is plus or minus 3 standard deviation. If you take 99.73% or 99% level of confidence or 1% level of significance, then this is your lower limit, this is your upper limit, and you can see now SCF is under control. Here also PSCF is under control. Now you can go ahead with your forecast. If you do not do that, then whatever forecast you do, it will be coming up with a lot of error, and that is one thing that is not basically needed, or it's not a desired, I should say. Then you have the ARIMA model. Here actually you are introducing something called the differencing, as I have shown you. So this is actually the differencing part. This is your AR part, like previously happening. This is your like MA part, okay, and you are integrating them with respect to the differencing. Then it is becoming ARIMA model. Okay, so this is your ARIMA model. Now ARIMA model will vary depending on the P, D, and Q. P is for PACF, you can say Q is for ACF, and D is for your differencing. That you take into consideration, that you can go for several iterations in your machine learning, and you can put it there to get you a good result. There also you have some code that you can perform, that auto ARIMA, that is also available. But before auto ARIMA, I suggest you to try with a few ARIMA models by fine tuning the parameters and see what is the result. Then your another bigger model. There actually the seasonal part is coming into picture. This is again P, and this is again D, and this is Q. So seasonal part is coming here, and P is equal to 4. P is equal to 4. So this P is equal to 4. That is the period that have been taken. If you want, you can take P is equal to 12. P is equal to 6. Whatever you want, you can take. Now here, this is actually, you can see there is one. First is starting with the AR model. Then AR non-seasonal, AR seasonal. Then your differencing, this is non-seasonal, then seasonal. Then your MA part, that is non-seasonal, then seasonal. Okay. Likewise, we need to proceed. So this is actually maybe something for seasonal part, maybe little advanced. You can probably try that. But in case you are getting into the time series in the forecasting analysis, you have no choice, I should say. Even though you find, some of you may find it is looking at the diversified background of the class, you may find little difficulty, or maybe difficulty to some extent. But there actually I'm helpless. So you need to slowly cope up with these things. All these things I've already explained. So let me proceed further. That's all. Then PDQ we need to find, and fine tuning the parameter. As I said, iteratively in the machine learning that you can take, and you can see your sum squared error should be minimized. Sum squared error, then you can say this is SSE. Then you can find MSC, that is mean squared error. Then you can find root mean square error. So all these things systematically you can find to see that your forecast is a good forecast. And that optimization part you can keep it aside, because in the Python there are default algorithms to give you the better result in auto ARIMA. If you are doing it yourself with manually, that fine tuning the parameters, you can check it with several PDQs. Otherwise, if you are going for the auto ARIMA, then the inbuilt code will give you the better result. I'm not sure whether it is the best result, but it may give you the better result. But for the best result, you maybe keep trying with the data part of it. Otherwise, it will be difficult. Now here the model performance. So I think some of you, or maybe most of you, are familiar with all this. The very simpler ones. But this one I'll be actually using mean absolute percentage error. So this is actually the deviation from the actual to the forecast. Then it is the actual. Okay, you just divide, then multiplying with 100 and taking cumulatively. And of course, there is absolute, because there is absolute term here. So this is one parameter, or you can say the model performance indicator, not parameter, model performance indicator. So then you have here the Bayesian information criterion. Okay, the Bayesian information criterion, basically, you are taking the mean squared error and the k-tens of this particular value, that ln n by n. So n is the non-missing residuals, number of residuals, and K is the number of parameters. So you do not have to really calculate it. If you can, if you are trying in Excel, probably you can do it. Then something called like a normal distribution. If you are doing it manually, you can probably check. That is not required. Yes, Python. So here you have another information, that is AIC, that is BIC and this is AIC, little refinement here and there. So it will be used in the model. Now, these are the few readings. I have not many. So readings for you. This is one thing that probably this is actually the core behind the forecasting models. You can say starting from the moving average to any model that you take, ARIMA, ARIMAX, whatever. Of course, our machine learning based things are a little different than that is, you can say your multi-layer perceptrons, or you can say the RNN based network. So there are several other things you'll be falling in line slowly once you get this particular faster differentiation of the forecasting model. So this is the book I was talking about. It's a good book. You can probably, if you're interested to make a career in this, probably this is. Okay. So now what is that I'm going to do now is basically the quick, because time is too short, I'll just take you through the Excel sheet. There also I will not be doing any kind of calculations. I'll just demonstrate. Then we'll straight away get into the Python part of it. So before we get into this part, I would like to take if there is any quick questions on this presentation or the demonstration part of it, so that I can proceed quick. Already 1 hour is over with respect to the presentation. I thought it will take 45 minutes. It has taken more time. Yes, quick question if anybody has.
So I would like request a participant. Do you have any queries, please?
Dr. Venugopal, actually, due to the paucity of the time, I am going little, above maybe the background of few participants. So
okay,
kindly, excuse me for that because time is too short.
Yes.
Yeah. So had it been ARIMA, then I would have only sticking to the ARIMA. But now you said forecasting model, so
yes.
I have really challenged to, do the justice to the topic that you have given.
Yes.
Okay. So this is actually, I'll just demonstrate. I'll not be really calculating anything. So before that, I'll just show you the data part. This is actually the data that I have taken from, the Ministry of, we can say, the Department of Cooperation. So this is actually the data regarding one commodity price. Okay, one commodity price.
Sir, one query in the chart box. Could you please?
One query in the chart box. Yes, just a moment.
The formula to take time series sample for this study.
Just a moment.
Dr. Sheikh Masood.
Just a moment.
Yes, sir.
Chart box.
Down, sir. Top. We can. You shared, no, sir.
No, this is actually. Here it is, right?
Yes,
yeah. No, this is actually all the participants. So, what is it? I think we need to. Just a moment.
Yes.
Hello.
Yes, sir. Yes, sir.
Sir, can you have any formula where for selecting sample for the time series analysis?
Any formula?
Sir, say for example, I need to forecast for a period of 5 years. So, okay. How many data samples have to take?
Yeah, that is what I said initially. I think you might have missed part of my presentation. What I said is basically 10 years data. Normally we take, but we may need to, find some kind of reference for that. There is nothing concrete as such. The higher is the data size, the better it is for the analysis, because you need to divide the data, right? If you are getting into machine learning, you need to divide 80%, 20%, 75%, 25%. So if you have smaller data size, you cannot really play with the numbers. You need more data. What I have done in this case is basically, and the availability of the data also you need to see. If you are working on, let us say, agriculture or maybe food processing, we basically have the standard data available maybe for last 20 years, and some cases maybe for 20 years. Okay, if you have, what is your work there? Are you working on the day-wise data or weekly data or monthly data, or you are taking yearly data. If you take yearly data, I think that will be very less for the analysis. If you are working for day wise fluctuation, you will have huge data, and you are working on some monthly data, like how I have taken it is I have taken 120 data points. So this is what I could collect, but I think another 4 or 5 years of data is available, but that is not consistent with the requirement, so I discarded that. Actually, what I'll be presenting is purely from one of my research topics, and you can probably see that. So there is no rule of thumb there. So you can probably keep trying with more data. That is what I suggest.
Thank you, sir.
Yeah. So what it is actually, this is one retail price of a commodity. So since it is one of my research topics, I'm just not disclosing a little information. So actually, this is the commodity price, and they're at the retail level. So this is the price, and I've collected, as you see, till 2020 December. I think in 2021 there are a few more data points available that I have kept for for extending my forecast, and for interpolating the results that I'll show you later. So this is actually the thing. So this is one data set where I'll be demonstrating you the results. Then here there's another data set that is actually a little bigger one, where I have taken, as per the availability of the variable in the commodity market, I have taken the arrival to the mandis, okay, across the country, and that I have taken in the country our country India. So there I have taken the total arrival across all the regions, across all the mandis or important mandis where the product basically or the commodity basically arrives. Then we have the wholesale price. Then we have the retail price. That is actually there are two things available in terms of the prices. So you can say this is like a proxy for your production. The arrival, unless you process it, that you can take as a proxy for your production. Then the wholesale price and the retail price. Now, the question is here, looking at this, 20, till 2020 data, starting from 2011, I've taken from January. You can see this is 01. 01 is January. So here you have 01 to 12. So this data you can see starting from 01 to till this is 12. So 12 months data that I have taken. Also, in some cases, the day-wise data is available, but day-wise data may not really work because if you want to have a very minute analysis, how the day-wise information is getting changed. Otherwise, month-wise data is also fine. So for my research, this was fine, and also the respective journal, they accepted it, so I didn't have any issue with the number of observations and all that. So this is actually one thing that I should say. So here I have taken 10 years data, and 10 years data means there are 120 observations. This is what is the time series data of time series monthly data that you can say. Then another series that I have taken, little interpolated one. So here I have taken that the third one. Here actually I have taken last 12 values. Last 12 values is actually for 2021. For my model validation, I have kept that data 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So till here. So till here, this is actually for my model interpolation, or you can say for my extended forecast, the future forecast. So we are now at, let us say, 2021 July, and I am interested to have beyond July, August, September, October, November, and December. So what will be the commodity price? So the interesting thing here is that if this kind of results are coming to the notice of the key stakeholders, you can say anybody can be a stakeholder, starting from let us say retailer till the government agencies or the regulatory agencies. So it will give some insight to everybody that how things are really happening, whether things are under control or things are not under control, what is the kind of intervention that is essential in the process. So those are actually a few things you can say. I'm getting into little the cross-sectional part of the study, but that is not the concern here, we'll just forecast and leave it there, and the latter part of it can be taken off as a cross-sectional study, because time series data will not be giving you many things. So you need to really get into the field unless you don't have much things to learn from there. So this is one thing. So these are the three different types of data sets I have just kept ready. So what is that I'm going to do is now, my hypothesis is, I'll just quickly show you how I'm getting into this. So as per the literature and my own field study and all that, even we also did a similar kind of work at IIM Bangalore. That was for a different commodity, that was the pulses. Okay, that was the pulses, and we took basically the red gram. You may be knowing that the tur dal, which is greatly consumed by more or less every Indian. So that was basically the study, and it was a kind of that is the study from CASI, that is University of Pennsylvania. So that we did there. A similar kind of the experience and the some literature support. I just took into consideration a few variables. So that is basically the what I should say in a very simpler manner. You can keep extending model. So the retail price is basically a function of, because unless you do some processing, the retail price is a function of your arrival, okay, then your wholesale price, okay, then your wholesale price. So wholesale price is something that you have, you can say the wholesale price, that is the upstream price, and the upstream price is does impact upstream price, does impact your the downstream price. And for little advanced learners and maybe people from econometrics are familiar with this. This is something called Granger causality. This is something called a Granger causality. Okay, GRNGER, as per the economist Granger causality. So this is actually this says that a time series depends on past values of itself. Okay, so if I say retail price is one time series, that depends on the past values of itself. That is one thing. Second thing is that if there is any other series on whose past values the series also depends. That means if I say retail price depends on retail price, also it depends on the wholesale price past values. If that is the case, you are able to justify the relationship, there you will find at least one of the coefficients is not equal to zero. Then what you can say is the retail price is basically Granger caused not only by retail price but also by other variables. Okay, that is a little advanced thing. I am not demonstrating in this particular class. If you have interest, you can probably Google the term. Enough material you will get. In case you need some query or something, you have some queries to ask to us related to your own research. You need some kind of extra help or maybe some hand holding, whatever. So you can probably contact us. Then what is happening here is I'll quickly. So this is my hypothesis. So with respect to this hypothesis, I am now getting into it. Since time is short, I'll just taking you through my calculations. So here, what is that I'm going to do is initially, let me increase the size of it. Okay, so this is actually the thing that I've taken directly from there. So this is starting from January 2011. Then here you have 2020 12. Okay, so this is actually the time series that we have. So what is happening here is initially what you can do is there are a lot of work for you, I should say. You can try with other methods that I have spoken to you earlier, moving average, exponential smoothing. I'll only demonstrate the Winters method and the ARIMA, whatever I spoke. Then what is happening here is basically, please pay your attention. Those who are, starting your, machine learning or maybe predictive analytics and all that. So please pay a little more attention. So this is the time, and This is actually if you want to write, if you're doing it in Excel, probably 1, 2, 3, 4 likewise. So 120 observations I have. This is actual data. This is not collected from any source or somewhere. This I personally collected this data and doing this analysis. And this is part of my research, and I am also demonstrating to you. So this is the time, and here the average retail price. Okay, these are the average retail price. If you want some diagram and all that, you can plot it, by insert chart. Not doing it. Then what is happening is, as I said, now you are deseasonalizing. You are deseasonalizing. So how we are deseasonalizing? Basically using this particular, criteria. So this particular criteria we have used here. You can also, I will share this Excel sheet with all of you. You can see the formula already I have demonstrated. I'm just executing in the Excel sheet like a clerical work I'm doing here, not much. So here, once I calculate my deseasonalized demand, now I calculate. So if your data size is very big, it will take a lot of time for you. You can replicate in, you can take a smaller data set, learn, and you can replicate in the Python. That will give you more insights. That is how I do the things, because I, being a person from mathematical background, I don't really get satisfied with only the codes. What happens behind the codes is my interest, not algorithm in the sense how the codes are written. That is not of my interest, but how things are happening with respect to the mathematical modeling. That is actually my concern. So if you are interested, that's fine. If you're not interested, you can simply straight away get into the code part and generate the output and go for your report or thesis submission, whatever. That's one thing. But for advanced learners, I'm just giving a little hint here. So deseasonalized demand. So you are deseasonalizing. This is the series that we got. And now the last two things we do not have the data, because it will exceed the data size. So we have to block here. You can see now this particular one is using C121. So that's the last. If you extend, let's say if you extend, it will be using C122, for which we do not have the data. So this is actually not correct, right? So we have to stop here before 2 and after 2. So we stop. Now this is actually one thing I'll just show you. This is a new series that we have created. This is a new series that we have created here. So this series, and we already have the time. If you can regress, then you get this intercept, that is a constant, and this is the slope. So using this intercept and the slope, we are finding the regressed demand. So this is the regressed demand. Now I'll show you one interesting thing. This is our observation. This is our observation. Okay, and this is our regressed demand that you have calculated. So you can see now there will be some change at least. See now the change. There is a drastic change. The sense now this part is more stationary than this. It has a lot of crest trough, like a wave. We all are familiar with the waves, how it happens in the you can say the rivers or maybe in the sea. So this is like a wave where we have the crest trough, but here nothing is there, right? So it is a better. Now the series has been converted to a better series. So if you do the analysis with respect to this, then your forecasting error will be less. So I could have done this, but it will take at least 30-40 minutes if I do it here itself. So I'm just demonstrating, and all the formula that are available in the box, or you can see you can keep the cursor and see how it is calculated. Not a big deal. This is your regression equation. So what is that I'm basically doing it here is this. Okay, it's a very simpler one. So this is what is my thing. So here your yt is equal to, or dt, whatever you say, 1525.93 plus your 19.2, that is t. So this is what is the model. It is a simple regression model. So once you do that, we are slowly moving into the Winters model, Holt Winters model. So here we have, this is the thing. So I calculated the regress demand. Then the seasonal factor. Seasonal factor, I have given you the formula here. The seasonal factor is the demand that we have, actual demand, and the regressed demand that what we have calculated, that you can say kind of a deseasonalized demand. If you divide these two, then what happens is that this comes with the seasonality, and this comes, little explanation, because this is one important step here. So this comes with the seasonality. This is actual data here, and this comes without seasonality, or maybe very less. We have reduced the seasonality part of it. So if you divide this, then you get the seasonal factor. Then you get the seasonal factor. So this seasonal factor will be helpful in the successive steps. So this is one part of the Wunder's method that, or the model that we have, we have executed. So now what is that is happening here is, to give a formula to calculate the seasonal cycle. Seasonal cycle is basically the long term. Okay, in the sense, what is happening in the period 1 here. That is, I have said that I have taken 4 periods: T1, T2, T3, T4. So then again T1, T2, T3, T4, this will again repeat. This will again repeat. That means after 4 months, the cycle will repeat. Cycle will repeat. Cycle will repeat. So here in this seasonal cycle, what is that I have done is I have taken the average of this one. This one, then you leave 3 from in between. This one, you leave 3 in between. Then this one, you get this one. Okay, that is the average. So I have just used a formula, average if T1. So that is the formula. So this is my, the seasonal cycle. And this cycle, you can see now, this is almost repeating. This is almost repeating. Can you see? This is repeating. I'll just put a mark here again. This, okay. Now you see this, they are all repeating. Okay, this is repeating. So likewise, you can see how things are interesting now and how they are repeating. So this is the seasonal cycle. So this is one part of your, one part of your work. So I should write here seasonal cycle. Okay. Then here you can get into forecast and error. Okay. So now what is happening? I'll just increase the size. So normally this method, when I do in the class or in any workshop, it takes not less than 45 minutes. So just to save time here, I'm just demonstrating because Arima, I need to show you. So this is actually the thing. Then this is, as I said, this is your level. Then this is your trend, and this is your seasonality. These are the 3 things I have already spoken to you while the theoretical framework I have given. So there I have spoken to you that this one here, level, trend, and the seasonal cycle. So here, these 3 things I am just replicating, LT, TT, and ST. Now, these 3 actually 3 different, these are 3 different exponential smoothing, models of their own. They are actually the exponential smoothing models of their own, in the sense, here we have introduced one alpha, and here we have introduced the beta, and here we have introduced one gamma. So you can do that, and the procedure is here. Procedure is here. Okay, it's not a very big deal. It is just a clerical kind of stuff that you need to execute. And after doing this, then you calculate the forecast. So forecast, there is a mixed model that is used. Okay, what is the mixed model? I have already told you. The mixed model is basically in the component part I have said here. The mixed model is the level plus trend into seasonal factor. You just multiply. So if you do that, you get this forecast. Now you know that is you have to proceed with respect to the 1 lakh. Here these are the informations used. So this is the forecast. Okay, first part we don't have the data, that is remaining plan. So then you just drag it. Okay, after you give one value that you calculate, so you drag it, you get your forecast. Now error, this is your this is your actual, and this is your forecast. So, or you can say forecast minus actual, you get this value. Doesn't matter whether it is positive or negative, because we are anyway calculating the absolute values. Okay, it will take some time for you to understand, but once you do it yourself, you will be thoroughly understanding. There will be absolutely no issues. Then we calculate the mean absolute deviation. So what is the mean absolute deviation? How it is calculated? that I have already shown you in the performance of the forecast. One more time, so you can see this. This is here. So this is mean absolute deviation. We are using this formula. Then mean absolute percentage error, you are using this formula. And of course, MSC and AIC, BIC and AIC, we have not calculated here. But if you want, you can probably do some kind of estimation. This you can calculate sigma. You can calculate 2 pi 2 into 3.14. All these things you can calculate. Doesn't matter. But in your Python, it will be shown to you. So now this is MSC, then root mean square error, absolute error, MAP, and this is tracking signal. That is, greater than 6 will be telling you that the model is overfitting, and less than -6 will be telling you that model is underfitting. So here I think I didn't mention that here, I believe. So less than -6, the model will be underfitting, and more than +6, the model will be overfitting. So whether it is underfitting or overfitting, these two are not, actually, wanted situations in our machine learning. So we need to pay attention to this. Then what happens is all this are calculated. Now the question comes is with respect to the forecast. Now the forecast is here. So I have forecasted for another you can say 12 months. Another 12 months. So this data which straight away take to my analysis. The results what I get in for other methods like ARIMA, ARIMAX, and so on. So these are my results, and these results I can compare, and I can see which model is basically fitting into the requirement of this typical commodity, and this will give some insights to the stakeholder to take a call and control the price. Now, so this is what with respect to the calculations with respect to the Wooter's model, and it is very good model. Most of the times it gives the better result. Now you can see one thing here. This is the MAP is just 20%. You can see this N column. This is just 20%. Okay, so this 20% is if you want to minimize. Okay, then I think I don't know whether it is done here. So you can get into the solver that we can get into data. Then in the under the data, you'll find solver. You have to add extension. I think I have done it here. So I'll just send you. You can see that. So the model is actually this is the non-linear gradient based model here that has been used. If you want, you can use also simplex. Okay. So many solver the models where I think less than 2010 version is available. I think it will be simplex, but more than 10 version it may be the GRG non-linear. This is another algorithm based on the gradient. Then what happens is basically all these values are less than or equal to 1, and they are greater than or equal to 0. So I just minimized. So I got the result as 20.70. So it is 21%. So whatever forecast I have done with respect to this, I expect that the model has a forecasting error of 20% or roughly 21%. 21% of the forecasting error is not a very high error, I should say. That means if I predict for 100, I'll be actually getting 80, or if I that is plus minus side of it, or if I have 100 and on the optimistic side, it may go up to 120. That is what is the the practice, or that is what is the mathematical derivation or the logical conclusion that I can have. Then this is one thing that I have done. So now I'll take you to my this one, the Python codes. We have hardly 30 minutes. Some questions will take, and so I have not done it, but still it has taken a lot of time. So now I'll get into this. I think Dr. Ganesh might have given you some insights with respect to this. Um, so this is Anaconda Navigator, and there we are using Jupyter Notebook. So I like Python the most because of its certain flexibility, and also industry it is greatly used. R is more of academic use. So Anaconda Navigator, I think you must have installed by now. So all these things I'll be sending you. You can, Dr. Ganesh asked me to send some material, but I couldn't send. Doesn't matter. So I'll be sending today. So you can, upload that file in your Jupyter notebook and you can run. Okay, so Jupyter notebook. So minimum 8 GB RAM is better for this kind of analysis. Of course, it is a smaller data, no issues, but when the data size is very big, some 1 lakh data points or 2 lakh data points, so then you need a higher RAM. Okay, so this is actually these are the two things that I'll be sharing with all of you here. Yeah, this is the one. I'll send it in HTML file or maybe in Python file. You can upload directly. So here, what is happening? Little bit size. Okay, I hope you are able to see the screen now better. So these are actually the few libraries that you need to load here or import from here. So this is actually the this is one thing for time series. All these things you might have already gone through. So date time, import date time. Okay, this is one. And the for changing the figure size and all that, you need some as a runtime configuration parameters. That's okay. Then statistical models. This is important. Cold winters, as I said, you need to import simple exponential smoothing. Okay. Then for starts models, you need SM. Okay. Then you need PACF and ACF. That is our plotting part of it. Then iteration tool that we need to replicate P, D, and Q. And then we need to import ARIMA model. Then ARIMA plus X plus seasonality, max model. And to calculate the mean squared error, that is MSE, that you need to find, MSE mean squared error. You can import this particular, what should I say, this library. Then something like with respect to the import, doesn't matter whether you keep it or not. So now quickly, I'll just show you this. If you want to do that in your, in your Excel, you can perform because the data size is not very big. Once you understand the concept, then you can do your analysis with respect to any data size. Bigger data size is not a problem. The problem is with the concept or the domain, how things are happening. That is very, very crucial. Then actually, I'm reading one data set that I've already shown you. I'm not writing any code for the time being because it will take a lot of time. I've already written and run this particular course yesterday, and I'll just demonstrate. And this file I'll share with all of you. You can just run it and see how things are happening. In case you have any further queries or something, that you can take it off. Here's the data. This is reading this is CSV file, and this folder I have stored, and this is the prediction underscore data 1. So let me run it. So before this, I need to run this, all the libraries. So library has run now. Now I'm reading this particular data. So this data I have shown you in my, notebook. That the notebook what I've shown you. This particular data I'm now reading. Okay. This particular data I'm now reading from Python. So now I have read it. Then I'm reading actually first 5. You do not need all of them to see here because already we have seen the data. So just to demonstrate, these are the 5. If you want the tail part of it, you can also see that. Then comes your declaration. The declaration actually you are declaring that the first column is actually the date and time. So this is called, that one code that you have to use, that is parsing. You have to parse the data with respect to the date and time. So when you do that, the first column will be declared as, the first column is this. This will be declared as, time, date and time. So let me run it. So this is date and time. Unless you do that, you will not be able to execute the other things. Then date and time I have declared, and the time, and this is the average retail price of the commodity that I have shown you. Then what is that you are going to do is, if you want to describe, you want to plot the minimum, data visualization that you can do. And what is happening here is, you can see now the exact things I think I have shown you in the Excel. You have seen there the same thing also I'm getting here. So if you want to describe with some basic statistics, minimum, standard deviation, mean, standard deviation, minimum, maximum, quartile 1, quartile 2, quartile 3. So all this you can see, and if at all you want them to use in your storytelling, you can take them. Then what happens here is now I'm getting into the moving average. So that is a very simpler averaging process. The domain part I have already shown you. So how you can calculate it is actually simply you can give this typical code here. So window is equal to 4. I am taking p is equal to 4, and I'm calculating the mean, like like how things are happening. This one plus this one plus this one plus this one divided by 4. So this is exactly what I'm running here, and I'm finding the mean. So you got all the means because you need 4 values to calculate the mean. So first 3 will not be taken into consideration. So you have 3 nuns, missing values. So those missing values you need to now remove for the quantitative analysis. So for that, what is that we are going to do is we are shifting this by 1. We are taking this and shifting this by 1. You will have another series to its next to it. So here you can see these are the 3 nuns, and you are shifting by 1. So there are 4 different series. The idea is we want to declare one as actual and another one as prediction. So that is the idea. Now, what is that I'm going to do is this is actually the first column that I'm defining as my data frame. That the first column is actual. Then the second one is the level that we have already calculated. As I told you, level is something that you calculate. That is W1 D1 plus W2 D2 plus W3 D3 plus W4 D4. Likewise, divided by W1 plus W3 W2 plus W3 plus W4. If you do that, you get your level. Then is the forecast. So this is our actual. Then this is our level, and this is our forecast. So then another. I'm just changing this nomenclature just to have a better representation. So this is the actual, and this is the level, and this is the forecast. So with minimum codes here, we are not using much codes, very, very minimum codes. So that we are using here, and you can simply copy and paste with your data, and you can run your data set. So in a very, very simpler manner, I have given here. So not to confuse you right from the beginning. Then we need to remove this nuns, all these missing values we need to remove. So for that, where from it is starting? First, second, third, and fourth. So it is actually starting from 5th observation. So that means 4 onwards, if I take, then my nuns will be removed. So I'll be straight away starting from here. So this is actually the data, you can say data kind of lacking here. I can't do any analysis with respect to this because I have all the missing values. So I can run this. Then you can see starting from May itself, all other values are removed. Likewise, I have shown you in this. The first one is not taken into consideration in the manual analysis because we don't have the data here, right? So we need to simply do it like this. And if you go for the manual calculations of a moving average and any other method, you will also be noticing that one. Then what is happening is quickly what is happening. Let me show you. So data I have I'm taking from the 5th row or 5th case onwards. I have read like this. So then my forecast is already over. Now let me tell you one thing. I think in the presentation I don't remember whether I have done it or not. The thing is that the moving average, then your moving average, then the exponential smoothing. These are the 2 methods. They do not take into consideration any kind of trend or seasonal fluctuation. They are neutral about it. They are purely neutral about it. If you take regression, it will take the trend part of it. Okay, and if you take ARIMA and higher methods, it will take both your trend part of it as well as the fluctuation part of it. If you take Wunder's method or Wunder's method in general, that also will take into consideration your trend as well as the seasonality. Okay, so this is one thing that you should remember. So in this typical case, what is happening is basically we have done that. So if you take for your analysis or you want to draw your inference, what is the forecast? Your forecast is basically this one, 5837 is your 5837 is the forecast that you can take. Since there is no seasonality, there is no trend, so forecast is 5837. It will continue. If you do it for 3 months, 4 months, or 6 months, you have to continue. If you are referring to other methods, there it will change. I just demonstrate how it will change. So this is actually the forecast part of it. Then you may be interested to know your, the model performance. The model performance. So the model performance, the mean absolute deviation, I have already shown you how to calculate. I am not getting into too much details of it, but already I have given here how you should calculate those things manually. Also in the code how it is calculated. So you can see from here. Then what is happening here is MAD, that is mean absolute deviation, is 980.79.
Okay, sir.
Please hold on. I'll get back to you. I'm running short of time. Let me demonstrate. Then I'll get back to you if there is any questions, please.
Okay.
So then MAP, mean absolute percentage error. There I have already told you that you calculate average percentage error. Then you take the absolute percentage error, that is APE. Then you take the mean part of it. So how it is calculated? I have given this. This is actually the library. And this is what we have manually calculated. If you can find any library, you can simply put there. If you don't find any library, so you can manually write your own formula there. Okay, that way I believe Jupyter Notebook is very flexible. So then you have your mean squared error. This is your mean squared error, and if you want to find the root mean square error, you can take simply the square root of the mean square error. So you get this. These are actually the model performance. Now, at this point in time, if you ask me what is the model performance, I may be little, in a problematic situation unless I get into the other models. But anyway, you can see now the mean absolute percentage error is quite higher. That is almost a 34%. Almost a 34%, so that I can say the model is not a good model fit. Okay. Now let me move to the second method. The second method is part of your Holt-Winters method. There actually we'll be using one model parameter, that is alpha. One model parameter, that is alpha. I think some internet problem. So now, before we get into this part, you can split the data. So you know how in the machine learning we divide the data: training data, testing data, and splitting with respect to the training and testing that you can do. But before that, I need to know my shape of the data. As I showed earlier, that I have 120 cases. I have 120 cases, and there is one column. There is one column that is excluding my time. I have one column that is the retail price. Then manually I am dividing. You can also bring that particular library here. Split train test. Split train test, and you can divide with respect to you can do that. But here actually I'm doing it manually. I'm taking my training data from up to 8 years, and the testing data for 2 years. Okay, this is what is I have done. So you can simply see. I'm not reading those data sets. If you want to read how it is happening, probably you can read it, but it will take your unnecessary space here. So I'm not reading it. All space is essential. So that is why I didn't show you. Only I'm printing the dimension. So when you print the dimension, it is 96. That is 8 years data I am taking for my training the model, and 2 years data I'm taking for the testing the model. Now the question here is it a good classification? That we need to, as a researcher, I should say, there is no rule of thumb here, but a majority of the researchers or the authors, they basically take 80-20. 80-20. In our operations literature, there is something called ABC classification, or 80% of the issues have been characterized by 20% of the problems. That is 80-20 rule that you say. So we take 80 here and 20 there. So that's a good, reasonably a good size. So if you have the less data size, yearly data, then you can imagine what will be the situation. We have only 2 data points. So that is, not advisable at all. So you need little bigger data size at least. Okay. So that's one thing. As far as my personal experience is concerned, the more is the data size, you can play with the numbers like anything. If you have smaller data size, then it will be, difficult. Then let us run it quickly. So this is very simple code here. The model is equal to simple X smoothing. Okay. And I'm using my training data. So I'm fitting the model underscore fit is equal to model dot fit, opening bracket and closing bracket. Okay. So I'm just getting into the model summary that you can see here. The it's optimized. The alpha value is 1. Alpha value is 1. That means if you take alpha value is equal to 1. So let me tell you, alpha value is equal to 1. Then what happens here is this part is completely ruled out. That means the prediction is purely based on your actual data, not on your forecast. So that you will say why it is happening, because it's the default algorithm is giving you the optimum result. It's giving you the optimum result. And how you can set your alpha and all that, maybe additional code is required, but I have not kept it here, so that you can probably try once you get into this result. But that is not required, because optimum result is always we need. We don't need something which is suboptimal, right? Little more information. Akaika information criterion, that is 1244, BIC 1249 or 1250, close to. Then the corrected AIC is 1245. So this, unless I get into other models, I cannot really conclude anything from here. So I need to refer to the other models. Now this the model is simple exponential smoothing, and it is optimized, and the initial level is 4198. Already you might have seen that. Then it is the model coefficient or the parameter alpha that is calculated to be 1 here. So this one thing. I'm interested now with respect to my performance. With respect to my performance, so let us get into that. So this is my actual data that I have declared as the test values. Already I have segregated. Here the test size is around 24. So you'll get 24 data points here. Then I need to pass this test data to my model. That is how the machine learning works. I think by now you might have understood, or maybe several other resource persons might have discussed in the class. You train the model, and after you train the model, you have the test data. Now you pass the test data through the model and see how the error part or maybe the other things happen. So we calculate the prediction that is actually the prediction that is 1636. If you remove this 0 part, then what is going to happen is you will get a prediction for 24 months. So all uniform. Because why it is all uniform? Because this model does not take into account any trend, any seasonal fluctuation. So it will be remaining as it is. So for calculations of my error, I will prefer to go with a single value. So now 1636 is my the value for the prediction. If you want to take it for, let us say, this is ending with the data is ending at 2020 December. So now you want to predict for 2021 January, February, March, April, May, June. They are they have already passed. Okay, then July is again going to get over. So you want to take for August. For August, what is that you need to take? This 1636. So this is your forecast. Now 1636 the forecast here, and the past forecast we got how much? 5837. 5837. Can you imagine? There is a huge difference. There is a huge difference. Okay. So now, anyway, when you compare the models, you can compare the models with respect to, not with respect to the forecast. We need to compare with respect to their, the performance indicators. They're nothing but the forecasting errors. So now let me get into this part. So the error calculations, or you can say the model performance. So now you see this is 48%. 48% is MAP. This is still higher comparing to the moving average. At least the moving average was giving a little better result, 34%. But here we are getting almost 48%. 48%. This is still, is very, very big, more than 15%. So this is not working fine. Now the question comes, as a manager or as a researcher or as a a regulatory agency, then what could be the better result that probably you can calculate, and based on which you can take the decision. Now, for that, I need a little more information. This is actually additional information I have given, for the benefit of the class. But straight away, you can get into the SEF. So let me show you quickly. This is what I'm decomposing. You can see now. This is your trend part. This is your original data. You have already seen how is the original data is behaving. So you've already seen, and this is quite similar or same as this. The first part. This is your observation, and this is your, you can say, this is here I have written the runtime configuration for the adjustment of this typical one. If you want to increase or decrease the size of the figure, you can do that. Then you decompose. Then what is the model here is being used? That is a mixed model. That is a mixed model. You can also try the additive model that I have shown you earlier while explaining the domain part of it. So here somewhere I have said here. Okay, all this you can experiment, but here and there you may have some problem with the coding because there is no single coding or something that will help you because RMO codings are a little different from RMAX codings with respect to the model fitting behavior. So there actually it will take a lot of your time. Even though so many things that I have been doing for the last several years, but still I get stuck up and take a lot of time in the night to execute. So there is no straight road to this. So it will be happening, and it is actually the part and parcel of any research. Should really enjoy this. Then the decomposition part is over. This is your error part. This is seasonal part. This is your trend part. Okay, we have decomposed this particular data, and if you want to see what is that is there in the decomposition, data that you can quickly run. You can see this decomposition data part. This is over and above the requirement. But just for your benefit, I have shown you the Excel decomposition part here. I've shown you. Okay, this is decomposition here also. Here also you are getting trained this one, and error part of course we are calculating here. Okay, all this here demonstrated here. Now residual part is coming here. Okay, now this is actually more than this. What is important is this part, SCF and the PACF. So now autocorrelation is something that is unwanted situation here in this case. As far as the higher order methods are concerned, like your RMA or RMAX or maybe any other model that you're using, maybe sometimes you can say for the Granger causality and all that, we need some additional information with respect to SCF and PACF. So you can see now, though the data, the first lag, second lag, please see my movement of my mouse on the screen. First lag, second lag, third lag, and the fourth lag, they're basically outside of the range. And within the range, this, if you say, this is actually the, you can say this is somewhere maybe, within 0.22 minus 0.2 to 0.4, and here it is 0.2 to 0.4. This is your confidence interval. Then what is happening? These four lags are outside of the range. Then the data is almost controlled. Then comes your PACF. So you can do the similar way. I don't know why two times the it is generated. Maybe you may have some answer, but I do not have any answer to this point in time. So the PACF you can see now this first lag, second lag, and the third lag. So almost they are outside of the range. That is the minimum and the maximum. That is the lower control interval or lower confidence limit and the upper confidence limit. Then you have these are exceeding. Then comes so PACF and SCF indicate that we have some issue with respect to stationarity. Now the question here is the next thing comes is that the differencing part. So differencing, logarithmic treatment, all that you can do, but RMO has the default mechanism to control that. In case you want to manually check how things happen, you can do that. I'll just show you the differencing part. So the differencing I'm just showing you, this is not needed actually. I'm just giving you a little additional information so that you will you'll be in a better position to run the model. So the differencing part, when you do that, Then this is the as a minus tk, so that will be the first difference. Yt minus yt minus 1, or you can say yt minus 1 minus yt minus 2. There's a second difference. Yt minus 2, yt minus 3. There's a third difference, and so on it will proceed. So I've just taken the first difference with respect to the period 1. That is the first period. This is not part of our regular code. So when you do that, there is a nan here. So that nan has to be removed so that you can read from past case onwards. Then if you want to plot, you can see now this is slightly better. But remember, this is just for demonstration. What is that I'm trying to say is with what order the ARIMA model will be used. Okay, it may be 1, it may be 2, it may be 3, and so on. That we do not know. That the model itself will be telling us. Just for some demonstration, how things happen, I have just shown you. Now you can see this is a better picture. This picture, you just compare this picture and this picture. This is definitely better picture. Now, if you go for one more differencing, I hope this will be controlled. Anyways, that we are not getting into. So you are one more time we are doing it for PACF. Now you can see the PACF. PACF also is slightly better. Let's say PACF slightly better. At least this part is controlled, so that we have seen the PACF part. Okay, at least slightly better image that you're getting. But if you want second order differencing, third order differencing, that you please continue. No issues, absolutely. Okay. Now with this information, now what is that I'm going to do is basically I am getting into the ARIMA model. I've already shown you the model. So what is that is little bit of coding that is giving you so much of information, but you need to understand what is really the mathematical part of the model that is of interest to us. It is not the algorithm how it is executed. So now this is the result that ARIMA 111. So if P is equal to 1, Q is equal to 1, and D is also equal to 1. Now we are getting here the AIC here 1486, then BIC is 1496, and Hanan Queen information criterion is another one for basically for we take for additional information related to the heteroscedasticity and homoscedasticity. So you have some information. Here you can see the coefficient. What are the coefficient and the standard error, their p statistic, all that lower limit, upper limit, all are there. So here you can see that it is using the log 1 with respect to the average. Then it is taking the moving average of another log. So here is the coefficient, that is a constant, minus 39.3905 plus 0.2203 of yt minus 1 plus 0. I'm not writing the model. You can probably write that. I have already given theoretical perspective. 0.2713 into ET minus 1. So that is the model. Now, after you calculate that model, now it is the model performance for next 24 months. I'm just doing it. If you want, you can make it 12 and execute. So I'm just running it. Next 24 months, I'm calculating this particular prediction. Then after I have this prediction, I can see the prediction is not a good prediction because this is slowly depleting. How I can understand that by calculating this particular one image. I can see this is something. This is something what you have is basically your the actual, and this is basically the actual, and this is basically your trend. Okay, or you can say this is how your forecast is happening. The red color is the forecast, and this one is your actual. So we are not doing a good forecast. So that is one thing for sure. Now, as I said, for calculating the MAP that I have already shown you here also in the code, that you can write a little bit of more code here. You need to define mean absolute percentage error. But one thing here, if there is any library available, you can probably explore. But I did not find any library with respect to this. So I have just taken this particular code that I've defined. So mean absolute percentage error, that is the difference between the test data and the prediction. Then we are calculating the test data and the prediction divided by the test data into 100. So that way we are calculating this MAP. So it is 68%. It is again very, very high. Similarly, you can calculate the MSC. MSC is also very, very high. So this clearly, this is not a good forecast. Okay. Now let me get into the iteration of the parameters. Time is too short. I think I may need to, wind off in another 10-15 minutes maximum.
Yes, sir. Please continue. Sir.
Yeah, I think it is little problematic things in the sense it takes always some time. That too,
Yes.
I have not even discussed many things in manually. So I just skipped those things. Still, it has taken more time. So now I am iterating the parameter. So when you are iterating the parameter, here you will be able to permute. You may have the idea of the permutation. So I am taking 0 to 3 is the range. P is for for PACF, and Q is for ACF, D is for the differencing. I am permuting them 0, 1, 2, 3. 0, 1, 2, 3. So these are the 4 different. Actually, this will be taking up to 3, not 3. So 0, 1, 2. Now 0, 1, 2. There are 3 values. 3 into 3 into 3, 27 iterations. So you can see now. I think this is 0 into. I think this would be 3 into 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I think 27 outputs are there. Okay. 3 into 3 into 3. This is like a permutation, and this is repeating. So these are the things. These are the PDQs that I can permute. Now the question is, out of these permutations, which particular PDQ is giving me the better result? Okay. That is my concern. So how to know that? I actually cannot try for MAP, MSc, all that. If you can take only one parameter, that is the AIC, that is Akaike Information Criterion, that the formula that I already have shown you how to calculate manually and all that. So if you can calculate AIC for all these models, whatever is the least, I can take that particular one is my best result. Now you can see, now the machine is trying to train. You will be getting the result slowly. If you have more, normally it has been seen, even from my experience, I'm just telling you that if you can take up to 3 lakhs, more or less you will get the result. More or less you will get the result. But in case extreme cases, you may have to go beyond. But anyway, so if you want to permute up to 4, you can also do that. Then this is the result. Now, what is the best result out of this particular part? The best result you can see here is this one, 1473. 1473, this is the best result because all are higher. You can see all are higher. 1496, 76, here 75. Okay, so this is the least. So the best model is 211. Now, rather than leaving the system to give me the output by auto ARIMA, I manually try with the 211. So let us see what happens with respect to the 211. So it's a very simple model again, that Sarimax is the code. Sarimax is the code or the algorithm that basically we are taking for training the data, that is data underscore train, and the model is 211. So now here you can see one thing. Sarima, S is standing for the seasonality, X is standing for the exogenous variable, independent variable. In absence of those things, the model by default will be converted into ARIMA. So I repeat, S is standing for, I just highlight, S is standing for seasonality, X is standing for exogenous. Now, in absence of seasonality, in absence of exogenous variable, the model will be converted into ARIMA model by default. Okay, so now this has become ARIMA model with order 211. That is why I have written here ARIMA 211. So now this is the output that we got. Little more statistics. We got it here. Now you can see this is the beautiful result. If you are from statistical econometric background or some other background where you are familiar with, a lot of information you have in a single table, lot of information. So you see now this is Sarimax 211, or you can say there is no seasonality, there is no exogenous variable, the model is ARIMA 211. So now this is log likelihood. People from science background or maybe mathematical background may be knowing how we calculate the likelihood. We take the first order differentiation, put it into 0, then we calculate solve for the first derivative, calculate the second derivative, put the value there. If the first derivative result is giving the second derivative result negative, then we say the curve has attained its maximum. If it is positive, we say the curve has attained its minimum. So these are the few things that are happening behind the scene, and this is purely for scientific research. I'm just giving you that orientation, but people from other backgrounds simply can you just say this is actually something that we need to maximize. We need to maximize. So when you maximize, that means the value should be, if it is negative, it should be less. If it is positive, it should be higher. So now this is actually AIC 1476. So 1476, as I told you earlier, we already got 1476. Then BIC, HQIC, all these values are received. Now this you can see, this is lag 1. So you can say 1.2495 into YT minus 1 minus 0.4785 into YT minus 2 or DT minus 2, whatever, plus minus 0.9999 into ET minus 1. That is what is the model. Now, for advanced learners, little more statistics. I have already told you that your Legend box statistics, which is greater than 0.05, means the model is a good model fit. Heteroscedasticity is also not there because the p-value is greater than 0.05. Then that means your constant variance is already achieved. Okay. For the advanced learners, I just give this insight. Then Jark-Bera test. It is actually a test which is combining the two different results of the statistics. That is the skewness and the kurtosis. So skewness and kurtosis that is little affected here is you can see from basic statistics, skewness is a little positive because skewness greater than 0. 0 point some value more than 0, you can say there is some skewness. Of course, that is not a real concern here, but kurtosis is a concern. Kurtosis, you can say there is a high peakedness. So that high peakedness will be responsible for the low tailedness. Then what happens is that your kurtosis is, you can say, if it is greater than 3, then you can say the curve is a leptokurtic curve. It's a leptokurtic curve. It's not a mesokurtic curve. So I think previously one participant was asking that particular question. Sorry, I don't remember your name, sir. So actually what you are saying is there the sample size. So this peakedness may be due to that particular sample size that we are not sure, but we need to check. So this is one thing. Then we got the result. Now the time has come for the model performance. So I got the predictions. Very simple code, not very critical code. You are predicting the the data, that is the test data. Test data is starting from 96 and it is ending with 119. So 24 data points, as you know that in the matrix somewhere last one is added, somewhere it is not added because the value starts from 0 in Python, and in most of the statistical software the value starts from the 0, not from the 1. So that is the reason. Then it is dynamic. Then once we got this prediction, then we got this result. That is my test data and my prediction, slightly better result. Then I'm going a bit faster. Then we are calculating MAP, slightly better. Then MSC, and that is 3162. Then if you want RMSC, that also you can find. Already the code I have already shown you previously. Then the prediction, I am now extending beyond my time limit that I have. Okay, so I am predicting. So for that you need start is equal to 120. That is 1st January 2021 to 1st January 1st December 2021. So that is what is the thing. You can see now here it is already shown 1st 2021, 1st 12 2021. So you get the result. Now it is almost showing the uniform result. Okay, maybe the default algorithm, but this may not be the case. All the times the values will change with respect to the seasonal fluctuations. Maybe the we didn't consider the seasonal fluctuation. That may be the reason why the results are all uniform. But let us not worry. But I can say that slightly better. Now, if you want to plot that particular one with respect to your original data, that you can plot it by by this operation concatenation. You are just adding these two different series and you can plot it. So data will be a beautiful chart. In case it is going like a curve, it will be better. But still, then this is my prediction. This is my prediction. So this is one that ARIMA, that is 211. That is the best result as for my Akaika information is clear. Now quickly, as you have already seen how the things are happening. I'll run this particular seasonal model, where the seasonal model is only this part you need to add. Seasonal order 211 and the frequency is 12. If you need to make the frequency 4, that also you can do it, no issues. But here actually I have taken 12. So let us run it quickly. This is same model like previous. Okay, so I'm getting better result. Here my AIC is 1316. Since it is a model which is basically taking into the seasonal fluctuation. Then all other things I have already told you I'm not getting into. Then I'm getting into my prediction. These are my predictions. You can see now they're all changing. I have taken, this is the test data prediction, right? Test data prediction you need because you need to pass those results through the model to check the accuracy part of it. So you can see now this is a better result you are getting, right? So the data and the forecast, they are going little, syncing with each other. Okay. Now I'm finding my MAP, more or less 48%, not a good result. Then it is also visible from this chart. Then I'm finding my mean squared error, so that is also still higher. Then I am interpolating my future, or I'm predicting for the future. So that is for 12 months. This is actually the different results I got. So here I got seasonal factor has been taken into consideration, and the results are little better than the previous one, where it is purely similar. Then you have I am just concaten, you using the concat operation just to plot it, nothing else. If you want to skip this, you can skip. So this is actually is just extending the data. You can see now. This is extending. This is my forecast. The orange color is my forecast, and this is my actual. And this is not within the range. Within the range is 2020 December. Beyond 2020 December is my prediction. Now there is auto arima operation. This is a library that you need to use. Depending on your RAM, it may take a file that is a pyramid arima that So this is model by default will be available for you. That is auto arima. Then it is now red. So you are just generating auto underscore arima. That's it. Then training data and seasonality is equal to 2. Then you can say this periodicity is equal to 12. That is M. The frequency you can say. Then this is P, this is D, this is Q. Then this is P, this is D, this is Q. That is actually seasonality, and this is non-seasonality. Summarize. Then very simple. So just you can summarize this particular one. You will get all the result like previously. So AIC is AIC, BIC are most similar, not showing any better result. But I think skewness has increased, but kurtosis has decreased to some extent. And the Zark Vera is still statistically significant in the sense the data does not show normality. Then using this particular information, I'm just getting into I'm just replicating this result. I wanted to take the prediction from there, but somehow it didn't happen. So I'm regenerating the result. So this is regenerating the result, almost similar. So I'm now going for my prediction. Then after the prediction, I'm just plotting it. I go a bit faster. Then MAP very high. Okay. Then MAC very high. Then my prediction. These are my prediction. You can see this is a useless prediction at all, because how the things are depleting in the sense. So it is not going to give me any result. So anyways, this is actually mathematical things we have basically no control. You can see now this is not a useful prediction at all. So this is how you can finish your arima and sarima part. Okay, so I just save this, and what you can do is you can copy into your upload into your Jupyter notebook, and you can run it. So first what you need to do is you just clear all the output. Okay, you just clear all the output, then you run it yourself. So that will give you a little more insight. So I just save it and I'll send you this one. Then comes quickly in another 5 minutes. I'll just wind up. Please bear with me another 5 minutes. So this one, this particular one here, the same thing. I'm doing it, but this is actually the model for Sarimax. Okay, so I'm adding this. Yeah, please. Please give me another 5 minutes. I'll just get back to you. I'm just adding one exogenous variable. So exogenous variable, I have already shown you that particular data. That particular data is here. This is the raw data that I've collected and converted into the CSV file. So here actually this is the production, or you can say arrival is the proxy for the production of the commodity. That is then here it is wholesale price and it is the retail price. So now these are the things, and as per my model assumption, I assume that my retail price is a function of arrival and the wholesale price, because anything changes in the wholesale price will be definitely felt by the felt by the retailers. Also, the consumers will be definitely paying more or less due to the change in the wholesale market. That is how the wholesale price and the consumer price work, and they are instrumental in calculating the inflation. So now what is happening here is basically I just execute quickly. I just read the data. Okay, the problem is I didn't read this fast. So all the important libraries you need to learn. So there is no need to if you are a computer science researcher, then probably you may be interested to learn all these codes, how it is written. They're actually the libraries, and each library will have hundreds of lines of code that actually at least I'm not interested with. But what is my concern is basically the mathematical formulation and the logical calculation, right? Then the data that I'm reading. So as you see, this is arrival, this is wholesale price, and this is the retail price. Now I am just doing one thing. This is actually that I'm reading, and I'm declaring that the first one is the date and time. Then here I describe that if you want to do that, you can see now 3 different series. Now the first column, first 2 columns are independent variable that I have declared as X, that I am giving the I log. Okay, I log this particular code to trace my the columns. Then this is actually second column, which is my dependent variable. So independent variable, dependent variable I have declared. Then I am just segregating. You can also use split file here. Split coding here. Split, that is you can say your training and testing data that you can split. Then what happens here is I'm using like the previous one change. If you can notice, this is the data, that is my training data, and this is my exogenous data, and the order is remaining same. Order is 1 1 1 1 1 1 12. So now I just generate. So that means this is a model where we have Sarima model plus independent variable will be coming into picture. So that is actually like your I can say like this. This is I think this Arimax or Sarimax. Sarimax will be actually how it will be happening. The Sarima model plus your summation, your beta j xj, okay, something like this. J is equal to 1 to n. These are actually the independent variables. Okay. So now,
hello, sir.
Yeah. Can you just give me some 2-3 minutes? I'll wind up.
Yes, sir. Yes, sir. Please.
Yeah. So please, then you can see now our AIC. AIC has controlled, or it has given a better result, 1166 in comparison with more than 1300. So this is definitely better. So after that, you have all these parameters we have already spoken. So here you have a little more things. You can see now the 0.1501 YT minus 1 minus 0.9995 ET minus 1, then 0.0860. This is the, you can say, the seasonal parameter again, and this is the seasonal parameter with respect to the error. And here is the main thing. Here is the your independent variable or the exogenous variable. This exogenous variable is highly statistically significant. Highly statistically significant. So I can probably conclude that it is not the price that the series has itself, or the like a Granger causality, the price of the wholesaling market, rather than the arrival, rather than I think no, this is the wholesale price. Yeah. So this is the wholesale price. So arrival doesn't really matter. So wholesale price, if due to something there is a change in the wholesale price, then of course the result will be felt by the the can say the customers. Then it is the same thing. I'm just replicating the prediction, and this is my plotting. You see how close my forecast is with respect to the actual, very close. Okay. Then similarly, MAP is expected to be very less, 12%. Then my MSC very less. Then I'm predicting for 2021. These are my predictions. I have taken a little more to have a beautiful chart. If you want to control, you can control here by restricting the data, but make sure that you have a data set to pass through this particular result, because this one we need to pass exogenous variable, you need to pass through this particular model, then only we'll be getting the result for the rest of the time. So the future prediction starting from here. Now uh, for my research paper, I found that actual price that I predicted some 3 months before is being realized now. So that is how is the beauty of this forecasting. But we have to do a lot of things in between to fine tune the parameters so that I can do that. Now you can ask, what is the use? There is a lot of use. Use means all the stakeholders need to know certain things. Then only the market will be under control. Otherwise, inflation will be very high, and when that happens, we know that who are the people who are getting benefited. But needless to say, it is not certainly the consumer, like people like us. Okay, so this is what is my conclusion, and thank you very much for your time, and I hope this has given some insight. Due to paucity of the time, I need to uh, cut short certain things. So I request you to get into those things and prepare yourself. Any questions or something we'll quickly take and we'll close, because already I have taken 20 minutes extra. That always
No, sir.
happens.
Session is very informative. I think participants also, they have given their feedback at chat box.
Okay, fine.
So I would like to request participant, do you have any queries? Now time for
where is the chat box? I'm not finding where it is.
Sir, I think
I think I need to stop the I think stop sharing. Yeah.
Yes.
Then only I think I'll be able to find. Yeah. So I'm just stopping the. Yeah. Now I am able to see. Yes.
Yes.
Yes. Of course, I'll share the. I'll quickly go through this. Okay. So thank you for your compliment, and I'll share very informative all that. Okay. Kindly share the notebook. Yes, of course, it's my duty to do that. Then any other thing that I need to share? Yeah, everything I'll share. Okay, everything, whatever PPT also I'll share. Everything I'll share. Okay, don't worry for that.
I would like request us to participant. Do you have any queries, please?
Any queries, please, quickly, because we are running short of time.
Yes, sir.
I already have taken 20 minutes extra, so Dr. Benny Gopal should excuse me for that.
No, so sir. It's really just going well.
Actually, it always happens, and since there are certain mathematical things, if you jump them, you will not be doing justice, to the concept.
Yes.
And being a person from mathematics, logical, derivation is very important to me. And the same thing also I actually convey to the participants or maybe whomsoever is coming to me. But people may say that no, this is not needed. Then probably I have nothing to say there. Yeah. So yeah.
So, I think.
Please quickly, if you have any questions, otherwise we'll stop now.
Please, I request you again, as participant. Do you have any queries, please? I think no questions. Okay, I would like request participant. Do you have? Please give me a feedback for orally.
Quickly, one or two. How was it? Was it very difficult for some of you to understand? Maybe one or two quick feedback. It will help me to fine tune my further things. Of course, Dr. Benugopal and Dr. Ganesh will be sharing the formal feedback. But more than the formal feedback, I believe in the informal feedback. So if you have anything to say, please, one or two comments. That will help me at least.
I would like request participant, please.
So maybe one or two comments that will help me to, fine tune myself at least. If anybody, any comment?
Yes, Shruti, madam.
Yeah, madam, please.
Good morning, sir.
Yes,
Yeah,
madam.
good morning. Yeah, good afternoon. Yeah.
Good afternoon, sir. Sir, my background is computer science, so I was just concentrating on the concepts. Although it was a very good informative session, but I, in my end, had a lot of network issues, so I could not get that continuity for me. So I am waiting for the resource material so that I could work on it more.
Okay.
Once more.
Yeah, fine.
Thank you.
Yeah,
Thank you
we'll
so
send
much.
it, madam. We'll send it everything.